All right, so we're going to look at section 4.3, which is on proving triangles are congruent using two different methods. SSS, which stands for side, 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 and SAS, which stands for side, angle, side. Okay, so previously this is what we did. Okay, to prove two triangles are congruent, we had to prove all the sides were the same and all the angles were the same. Now, if you do it that way, that's the definition of congruent triangles. Three sides, three angles, they all match. But then that's 6 separate statements you have to write down. Okay, that's a lot of work. So we're going to come up with a shorter way to prove this. And one way we're going to do it is called the side, side, side postulate. Okay, what's a postulate? Or how does that differ from a theorem?
It's like a known fact that you don't have to prove.
Yeah, it's going to be a fact we don't have to prove. Okay, so proving triangles are congruent with side, 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 it's a postulate. Okay, we don't have to prove why this one works. Okay, but the idea of side, side, side is if you got 3 sides in one triangle that are congruent to 3 sides in another triangle, that's all you need when the triangles are congruent. Right. So all we have to do is prove that 3 sides in one triangle match 3 sides in another. When we get to side, angle, side, SAS, that will be a theorem. Okay, if we have time, we'll see. Maybe we'll prove it. But side, 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 that is a postulate. Oh, you know what? I'm sorry. Side, angle, side, that's also a postulate. So nope, we're not going to have to prove side, angle, side either. It's angle, angle, side. That's a theorem. That'll be tomorrow. Okay, so both the ones we do today are postulates. Okay, so there's an example of side, side, side. Okay, remember those little tick marks on there? Those mean that your sides are congruent. So in this case, NM and RQ are congruent. MP and QS are congruent. And SR and PN are congruent. Okay, when you name a triangle, remember we got to be careful with that order. Okay, make sure that you're consistent. You could name these NMP and RQS. Okay, that's one way to do it. Or if you start at P, you could say PMN and SQR. Okay, there's a different way to do it. Okay, any question on what side, side, side means? Okay, that's basically it. So you just have to prove that 3 sides are the same. Okay, so here's our first example. I want to prove that triangle PQW is congruent to TSW. First of all, any question on how I picked that order? Why, if it's a P, a Q, and then a W, it has to be TSW? Yep.
Because you have to do it so the line match up. So PQ is because PQ is congruent to an angle to line TS, so you have to make sure all angles.
Yeah, you gotta match everything up. So P, that's where your side with 1 and 2 came together, 1 tick mark and 2. So then go with the angle where 1 and 2 come together, T. Okay? Next we went to Q. That's where sides with 1 tick mark and 3 tick marks come together. So then go to the other one. Look where 1 and 3 come together. That's S. And W, that's where the side with 2 and 3 comes together. And that point is shared by each triangle. Okay, so it's the same in each. All right, so let's start out with our statements. Okay, I want to prove that these triangles are congruent, and I want to use side, side, side. This is going to be a 4-step proof. What would be, or actually maybe you could do it in 2 steps if you combine some things together. Okay, but what's one thing I could say based on that diagram? Yep.
PQW is equal to TSW, or congruent.
Well, that's what we want to prove. So you have to give the reasons why. And one of the last reasons is probably going to be the side-side-side congruence postulate. But we can't use the side-side-side congruence postulate until we say something about all three sides. Yep, one at a time.
Side PQ is congruent to side TS.
Okay, so PQ is congruent to TS. Okay. Anything else you can say kind of along that same reasoning? Yep.
PW is also congruent to TW.
PW and TW, yep.
And then QW is congruent to SW.
Let's see. QW, SW, yep. What's the reason for all of that?
It's shown.
It's shown, or what do we normally say when it's shown?
Given.
It's given. This is all given. Second step, and this will be our last step. We've now proven that the triangles are congruent. Okay, so now we can say that the statement triangle PQW. And make sure when you're writing congruent statements, you don't use equals. Okay, make sure you use congruent. So the two triangles are congruent. PQW is congruent to triangle TSW. And what's the reason? This is a new reason we've never used before, but we just learned about it.
The side postulate.
Yep, it's the side-side-side congruence postulate. We are going to learn some similarity postulates later on that have 3 letters. So we'll just make sure that we say it's a congruence postulate. Similarity comes much, much later. That's it. Okay, so you can see just by using this theorem, it's a lot less work. Okay, we did the whole proof in 2 steps. Now, you could have written this out as step 1. You could have made that 3 steps. The reasons would have been all given. But if you're going to have given for the same thing 3 times, I would just put it all in 1 step. Any question on that? Right, so the triangles are congruent. So what could you say would be equal? Something is equal here, but it's not the triangles that are equal. You could say the measures of the angles. Okay, the angles themselves are congruent, but their measures are equal. That's one thing. Yep.
The measure of their sides are equal.
Yep, and the measures of the sides, the length of the sides are equal. Okay? So equal always applies to something numeric, the measure of an angle or the length of a side. Congruence can apply to figures and shapes, not numbers. Okay, any questions on that? Okay, so as we just said, the side-side-side congruence postulate, it's a shortcut to prove 2 triangles congruent. And here's another postulate. Sometimes you don't need to show all 3 sides of the same. You always have to show 3 things. But here's another one, where you're showing a side, an angle, and a side. So basically the side angle side congruence postulate says that if you can show you've got 2 sides and the angle between the 2 sides in one triangle is congruent to 2 sides and the angle between those 2 sides in a different triangle, then the triangles are congruent. Okay, so let me put up a picture of that. Okay, so here's a picture of side angle side. So you got to show 2 sides match. So we got the one with 1 tick mark and 1 tick mark. The bottom side with 2 tick marks and 2. So now you've got a side and a side. Well, this time we don't have the 3rd side. It's not labeled anyway. But we do have an angle marked as congruent. And it is important that the angle is between between the two sides. Okay, if the angle was, say, the one up at the top, that it wasn't between the two sides, that doesn't work. Okay, that one is not going to be a congruence postulate. And its abbreviation, the way you can remember it, doesn't sound very nice either. If you had an angle, side, side, that's no good. Everyone see the abbreviation there? Angle is A, side is S, side is S.
Yeah.
You got it? Okay. So that's how you can remember that one. If it sounds impolite, it's not a congruence postulate or theorem. Okay? So you got side, 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 angle, side. So you got two. Tomorrow we'll learn two more. But ASS will never be a congruence theorem or postulate. Okay? Some people think it works, but it doesn't. All right, so let's prove that these two triangles are congruent. Now you can do it either way. You can try to do side, 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 if you think you have enough information for that. Or you can do side, angle, side. Again, if there's multiple information in a given, you can break it out into multiple steps. But I think we'll combine it if we can. Anyone see anything that we could say here that would start to get us in the direction to prove that these triangles are congruent? Yep.
The line BE and EC are congruent.
BE. Okay, BE. So I'm just going to do it in the same order. You went third, second. I'm going to go third, second. I'll say CE. So BE and CE. Okay, anything else we could say?
And like AE and ED or AE.
So yeah, AE, so he said first letter, second letter. Then in the other one, I'll go first letter, second letter, DE. What's the reason for both of those? Yeah, that's all given. Okay, so now we've got side, side. Now we got to decide if it's going to be a side, side, side or something with side, angle, side. Okay, anything else here? I think we've done everything that's given. But there's something else we can do here. Yep?
Angle 1 and angle 2.
Yes, angle 1 is congruent to angle 2. What's the reason for that? What kind of angles?
Vertical angle?
Yeah, they're vertical angles. Exactly. Okay, they form that X shape. Vertical angles are always congruent. So that's actually definition of vertical angles. If you wrote vertical angles, that's okay. Okay, so definition of vertical angles. Do we have enough information to prove those triangles are congruent at this point?
Yes.
Yep, we do. We have two sides proving congruent. We have an angle between them. Which theorem is that? When you have two sides and an angle between. Sorry, it's not a theorem, it's a postulate.
Side, angle, side.
Yep. So now we can say triangle AED is congruent to triangle DEC. And as Ian just said, that's the side angle side congruence postulate. Okay, so I'm being pretty formal about how I write it. On a test, if you write SAS, that's okay. Side angle side. Okay, any question on that one? And that's it, that's the whole proof. Okay, now that we know that those triangles are congruent, okay, you've proved them congruent. What else could you say now that's not given in the picture? You've proven that those two triangles are congruent. So now we can say even more about them. We don't have to here, but
AB and CD congruent?
Yep, AB and DC are congruent because those triangles are congruent, and that would be because they are corresponding sides in congruent triangles. Right, and we learned earlier that corresponding parts of triangles that are congruent are the same. They come out equal. So we'll have an abbreviation for that. Corresponding parts of congruent triangles are congruent. CPCTC. So we can abbreviate that. Corresponding parts of congruent triangles are congruent. Right? We're not quite at that step yet, but if you can see that, now we know that angle B and angle C are the same, and angle A and angle D are the same. Reason? Corresponding parts of congruent triangles are congruent. Okay. So that's eventually where we're going. Okay, sometimes it helps when you look at the picture to try to figure out which method you think you might use here. Does this look like it's going to be a side angle side problem or side side side? Which way do you think we're going to end up trying to prove that? Yeah? Yeah, we are going to use side side side. Right? Sometimes when you start a proof, you don't know. You're not sure how you're going to do it. You just kind of start and you see what happens. But now that, side, side, side is that correct method. So we're going to have to think about something with PR, because that's not marked. Okay, everything else is. So let's write what's given. Okay, somebody different, give me the two things that are given here. Denver? QP, okay.
And SP.
QP and SP, yep. What are they? Okay. Anything else? Somebody give me another statement that's given. Katrina? Yeah, QR and SR. Those are also given. Okay, so once you get two sides that are the same, you're more than halfway there. You're almost done proving that they're congruent. So now, this is the point where we have to decide, are we going to try to get angle Q and S? Well, that's what I'd need for side angle side, but there's no marks on Q or S. So I can't really use them. So we got to do side, side, side. Yep?
Could you just say that PR is shared between the two triangles and the line shared between the two triangles, so automatically they have to be congruent?
Yes, that's the basic reason. And if I was going to explain it out, that's exactly what I'd say. So side PR in the first triangle would be congruent to side what in the second triangle? PR. PR is congruent to PR. There's a name for that. Something equal to itself. And this property we've studied it in a group of 3 properties for many different things. We did it with angles, segments, triangles, parallel lines. Yep.
Reflexive.
Exactly. Perfect. That's the reflexive property. Okay, so I think this is one of the first times we've used the reflexive property in a proof. A lot of times when you just write down something's equal to itself, you're like, well, where would you ever use that? Right here. Right? Side PR is congruent to segment PR. All right. So now we're done. We've proven that all 3 sides are congruent. So triangle PQR is congruent to triangle PSR. And the reason? Side, side, side. Okay, and that's a postulate. Side, side, side congruence postulate. And that's it. Okay, any question on that? Okay, so there will be some proof similar to this on the test. Okay, this section really, it is all proof. Okay. All right, why don't you try that one on your own? Okay, you're given that segment DR is perpendicular to AG. RA and RG are congruent. I want you to prove triangle DRA is congruent to triangle DRG. Okay, to take a couple minutes, see if you can prove that. All right, so they asked us to prove these two triangles are congruent. Okay, you can really you could do any kind of proof you want. We'll stick with the statement reason. Okay, for most of our proofs. Okay, anything that I can say right away? Anybody see anything there? Yeah.
Segment RA is congruent to segment RG. That's given.
Yep, RA. Segment RA is congruent to segment RG. Good. And that is given. Okay, there might be something else that's given we could combine in that step. Anyone see anything else, Sarah? Okay, so that was also given. DR is perpendicular to AG. Now, indirectly, that might mean something else, but we can't say what that means till we say that they're perpendicular. Okay? And it's the same reason, given. All right. Could we stay for step 2? I think the RA being congruent to RG, I'm not sure you can do much else with that. That is what it is. But the fact that we have some segments perpendicular, that might mean some things. Yep?
DR is congruent to DR.
Okay, we have to say that eventually too. That's separate from the perpendicular angle, but we could say that now. So DR is congruent to DR. And what's the reason for that? What's our reason there?
Reflexive property.
Yep, that's the reflexive property. Now, if I had known we were going to say this statement next, I might have done something a little different. Generally, if you say something in the given, it's because you plan on using it right away. Okay? This statement that DR is perpendicular to AG, we said it, but then the next statement doesn't really have anything to do with it. That's okay. And again, I'm not going to be overly picky about that. But what I might have done is moved DR as perpendicular to AG as a separate step then. And then that would have been step 3. And then step 4 would have used it. Okay? So step 2 has nothing to do with the second part of the given. But the way we wrote it, it's okay. That is okay. Now we got to use that fact that they are perpendicular. So what does that mean? If DR is perpendicular to AG. Yep.
Angle DRG is congruent to angle DRA.
Okay, I think we got to say one thing though before we can say that.
Their measures are equal.
Yeah, or we at least have to say that the angles are congruent. Before, well, we have to say something about the angles. What kind of angles are they?
Right angles.
Yeah, they're right angles. Okay, so angle DRG is a right angle. The reason? That's the definition of perpendicular segments. Or if you wrote lines, I guess that's okay, but we really don't have lines here, we have segments. So, definition of perpendicular segments. Okay? They form right angles. Okay, now we know angle DRG is a right angle. And because of that, DRA is also a right angle. Okay? Why? That's the definition of perpendicular segments. Okay, we're just kind of extending we had a statement that said if you have perpendicular lines, they form 4 right angles. Well, we don't have perpendicular lines here, but we do have perpendicular segments. So it's based on that theorem. Okay? So in this case, perpendicular segments form 2 right angles. Okay, so angle DRA is a right angle. Okay, let's check and see what the book does for a reason on that. Okay, the book actually, they did say that if you have 2 perpendicular lines, that they form 4 right angles. Okay, I wasn't going to use that because I didn't think DR and AG were lines. They're segments. But that's how the book did it. So that's... If you have, and there was a theorem number for this, but I don't remember the exact theorem number, so I'll just write it. If you have perpendicular lines, they make 4 right angles. Okay, step 5. What do we know about angle DRG and DRA? Their measures are equal. Even before that, what would you say? They're congruent, yeah. So angle DRG is congruent to angle DRA. The reason? All right angles are congruent. Okay, that was the right angle congruence theorem. So all right angles are congruent. Okay, now let me check off the 3 important things here that are going to help us out. Angle DRG is congruent to angle DRA. DR is congruent to DR. And RA is congruent to RG. Those are the 3 things that are really going to prove what we want to prove. So what postulate proves these 2 triangles are congruent now? Using the 5 things checked off in red. Yeah?
Side equals side.
Yep. We've got a side. Step 5 is the angle. And step 2 is another side. So step 6, state your congruence. Triangle DRA is congruent to DRG. And the reason? Side angle side, congruence postulate. Okay, any questions on that? Okay, again, a little bit more work because they didn't directly give us 2 angles that were congruent. We had to work with that perpendicular statement. But it wasn't maybe 2 extra steps than normal. So not too bad. Okay. Anything else on that proof? All right. So this kind of proof is something we're going to spend more time on. It's called a coordinate proof. And I think coordinate proof is actually easier because with coordinate proofs, all you have to really do is measure distances using the distance formula, okay, to do this problem. All right, so I want you to show that these 2 triangles are congruent using side, side, side. Now, if we know a little bit of trig, we actually could find some angles here, okay? At this point, we don't know trig yet, so we can't find these angles. But that's okay. They didn't ask us to. They asked us to use side, side, side. Okay. So how many times are you going to have to use the distance formula here? Well, 3 for each triangle, right? So how many total? 6. So you're going to have to find the lengths of 6 sides. Some of the arithmetic is going to be very easy, especially for the horizontal and the vertical segment. The diagonal one, that might come out to a messy answer. Okay, so try that. See if you can find the lengths of the 3 sides on the left, the lengths of the 3 sides on the right. And when you use the distance formula, that's a formula. Okay, that proves that the length is what you said it is because you use the formula. Okay, we can't just count. Okay, especially the ones that are on a diagonal. So just try using your distance formula and see if you can show that.
Couldn't you automatically assume if 2 lines of triangle are congruent, then the third line automatically has to be congruent?
Yes, that is one of these things.
So well, we did learn that about angles. If 2 angles are the same, then the third angle has to be the same.
Well, in a triangle, you know it's going to be three lines, right? And if 2 lines are already the same, then there's only like the 2 points in between those lines that don't connect, they have to be the same length.
Right. If you think about it with like if you use the Pythagorean theorem. Okay. Now the Pythagorean theorem only applies to right triangles. We don't know if we have right triangles here. It's not marked that way. It looks that way, but it might not be. But if you think about the Pythagorean theorem, if you know A and you know B, there's only one answer that C could be. Let's say A was 2 and B was 3. Well, C can only be one number. There's only one answer for the third side. So yes, if you do prove that 2 sides are the same, at least in a right triangle, then the third side would have to be. Okay? Whether or not that works for all triangles, maybe we could think about it a little bit. We don't have a formal proof of that yet, if we're going to get to that. So for now, you just have to show all 3 sides. But that is a good thought. And it definitely would work, and I can show you why for a right triangle. All right, so after coming back, I think we showed that in general, having 2 sides congruent isn't quite enough information to prove the triangles are congruent. Okay? But in a right triangle, then it would be. All right. So let's just write down what our distance formula is. Okay, what is the distance formula? How do you find the distance between 2 points? Okay, what does it start out with? Yep.
Rate times time.
So that is distance, but this is for coordinates. So to find the distance for coordinates, anybody remember how that starts out? Marquise?
It's AB equals x2 minus x1 squared plus y2 minus y1 squared, and it's all that is squared.
All of that is squared?
Square root.
Square root. Perfect. That's exactly what the distance formula is. Okay, in case you didn't know it, that's really just your Pythagorean theorem. Just written with coordinates. All right, so let's find our distances. Okay. We'll find all 3 distances on the left, and then maybe the horizontal and vertical on the right, because they are, if this starts to get too repetitive, we will just count them. But we'll find GH directly, because that's a little tricky on the diagonal. Okay, let's start with AC. All right. So remember, when you write down and you don't put the bar over it, this means the measure of AC. Okay, so let's look at our coordinates. It's -7,5 and -4,5. Okay, so I'm going to subtract the x's. So let's go -4 minus -7. Square it. plus, and now subtract your y's. 5 minus 5. This one's going to be pretty straightforward. What happens when you do 5 minus 5? 0, and then you square it? 0. Okay, so that part just crosses out. Okay, Kiara, what's negative 4 minus, should be negative 7. The reason I had to fix that is because we had a minus from the formula and another minus from the number. So what's negative 4 minus 7? Well, what's going to happen when you subtract negative 7? It becomes what? Go ahead, Kiara. Yeah, it becomes addition, so it's negative 4 plus 7. 3. Okay, so that's going to give me square root of 3. And don't forget, on the outside, there's that exponent. You still need to square it. Okay. Well, since the second part canceled out, what's going to happen, this really simplifies. When you take the square root and square, what do those two things do to each other? Yeah, they cancel out. So after all that work, all you end up with is 3 units. Okay. On the other side, we'll just count that. We could use the formula, but we don't need to. Okay, let's find AB. Okay, let me just copy down my coordinates. So it's negative 7, 5, and negative 7, 0. All right, so fill the formula in. Subtract your x's. Negative 7 minus negative 7. Don't forget to square it. Okay, I put that second negative 7 in parentheses because it's kind of confusing when you have the two minuses next to each other. So hopefully that looks a little clearer. And then the second part, let's do 5 minus 0. Okay, what do you get when you do negative 7 minus negative 7? Connor? 0. Becomes negative 7 plus 7. That's gone. Okay, so we're going to get the square root of, what's 5 take away 0? Just 5. And when you take the square root and square something, they cancel out. And all you're left with is a length of 5. Okay, again, we won't do those easy cases on the other side. All right, now let's do the one that doesn't come out quite as nice. Let's find the length of, let's see, we have AC. AB, let's do BC. Okay, so our coordinates are negative 7, 0, negative 4, 5. Okay, what's going to go first? Somebody tell me I'm going to have what minus what? Denver? Right here.
Oh. So it's the negative 4
Yep.
minus negative 7.
Yep. Negative 4 minus negative 7. And don't forget, square that whole thing. Plus, and who can tell me what's going to come next? Selena? Yep. And what do you have to do with that? Square it. Okay, so we've done both of these calculations earlier. Okay. Negative 4 minus negative 7 becomes negative 4 plus 7, which was 3. And then 5 minus 0, that gives me 5. Squared is 25. So add them up. 3 squared 9, 5 squared 25. What's 9 plus 25? Marquise? 34. Good. Okay, so now we've got all 3 lengths in one triangle. All right, let's find the side that would correspond to AC. Okay, what would be the side that corresponds to AC? H, yep. FH, sure, let's find FH. Okay, this time, because it goes in a straight direction, you're going to get one of them canceling out to be a 0 in your distance formula. So let's just count it. So it's 1, 2, 3 units. Okay, how about the side corresponding to AB? What's the side that corresponds to AB? Connor? G, F. Yep, it's not. We could say FG if we were going to do it in the same order, only because I started where the side that 3 and 5 came together. So we do F, and then towards that point G. But that's fine. Okay, FG, we can just count. Okay, we've got 1, 2, 3, 4. It's 5 units long. So I'm just saving a little time, so we don't have to go through the distance formula 6 separate times. And our last side. Okay. What's the side that corresponds to BC? Marquise? GH, good. Exactly, GH. Now GH, because it goes on a diagonal, you can't just count. Okay, we got it. Let's use the distance formula, and this will be our last one. All right, so G is 1, 2, H is 6, 5. Okay, James, can you tell me what's going to go in my first set of parentheses?
6 minus 1.
6 minus 1, perfect. Plus
5 minus 2.
5 minus 2. And remember, we're hoping to get square root of 34. Okay, let's see what we got. Okay, Ian, what's 6 minus 1? 5. Okay, Jacob, 5 minus 2. 5 squared is 25. 3 squared is 9. It's exactly what we had before. Okay, square root of 34. Okay, so we've shown that GH is the same as BC. We've shown FG comes out the same as AB. And we've shown that FH comes out the same as AC. Okay, again, kind of a repetitive proof, but that's how you can do a side-side-side proof on a coordinate grid. So, all right, side-side-side, triangle ABC is congruent to, okay, what would it be congruent to? See if we can name the angles corresponding. Start with just A. What angle corresponds with A? Yep. Yeah. A is where the side that's 3 and 5 come together. So look where 3 and 5 come together. F. Okay, let's get angle B. Okay, angle B, that's where the diagonal and the side that's 5 come together. What angle would that be in the other triangle? Yep. The diagonal and the 5 meet at G. And what's the only letter we haven't used? FG. Dakota? H. So that has to match up with C. Okay, any questions on that? All right, yeah.
That was pretty long.
Yeah, that takes a while. It is pretty repetitive. Okay, it can come out worse too if you don't have any points that are horizontal or vertical lined up that way. then you got all points on diagonals and they all come out messy. Okay, but they tried to help us out a little bit there. All right, so I'm going to give you the last 15 minutes to get started on this. Okay, so page 216. 6 to 11 odd. 6 to 11 all. 14 to 17 all. On 21 to 23 all and 25, you can use a 2-column proof. They ask you to do something different. Just stick with the way we've been doing it. And 33.